Hello students, in this module I'm going to introduce you to the fundamentals of partial differentials, or what one may call functions of many variables. Okay, so let's very quickly briefly recap what we know from functions of single variables. Suppose you have a function y is equal to function of x. Okay, you know that this can be represented as a graph of f of x versus x. It can be some function. We also know that the derivative of y with respect to x is the slope of the curve, the local slope of the curve y of x. Okay, this is something that you know from high school calculus. Okay, now in chemical engineering applications such as transport phenomena and fluid mechanics and thermodynamics, it's often important for us to consider not just functions of one variables, but we have to consider functions of many variables. For example, you may have temperature in a slab as a function of the position coordinates x, y, and z, and in addition you may also have its dependence on time. In thermodynamics, you have, for example, pressure as a function of volume and temperature, internal energy as a function of entropy and volume, and so on. So functions of many variables are more a norm than exceptions in chemical engineering. So we have to understand a little bit about the calculus of functions of many variables, and that's the objective of this module. So to begin with, let's understand functions of two variables. Let's understand the two variables, the independent variables to be, let's assume the two independent variables to be x and y. So by independent variables, we mean the variables which can be varied at will. They are not constrained in any sense, and z is the third variable, which is a function, or what we mean by function is it depends on the values of x and y. So just as we just saw that you can graph the function of single variable like shown here, you can also graph the function of many variables, but unfortunately you need a higher dimensional space to graph these functions. So in the case of functions of two variables, where z is a function of x, y, you can consider a three-dimensional plot of x, y, and the dependent variable z plotted in the perpendicular direction. So in general, the function f of x, y represents a surface, a complicated surface. I'm just schematically showing it in the in the three-dimensional plane. Okay, so this is the function is actually a surface in 3D plane, just as a function of a single variable is a line. Okay, so in this case, therefore, if you take a cut at constant x, that is, if you fix a value of x and then you take a cut, let's take a cut at this value of x, then you will see that the function of two variables at a given value of x, some constant value of x, becomes effectively a function of one variable. So we will have z as a function of f of x, which is kept to some constant number, and y. So it essentially becomes a function of single variable y when you fix x to a constant. Okay, so now we can find out what is since it's a function effectively of one variable, when you keep x constant, you can ask questions like what is the slope of this curve and so on. So you may say that the slope of this curve is dz by dy for this constant value of x. So this is something that we can do very easily. Okay, now in reality we cannot just assume this derivative to be a usual derivative, because we are obtaining this derivative by keeping x, one of the independent variables, to be a constant. Such a derivative is called a partial derivative of z with respect to x, or in this case the example I gave, we considered x to be a constant. So this is how z is varying with y provided x is fixed to a given number, and this partial derivative itself, okay, is a function in general. Partial z by partial y is in general a function of both x and y. Why does this happen? This is because here x is considered to be fixed to a number, but in general that number can vary. So the value that you get for partial z partial y will also depend on the number that you fix for x, the constant number. Therefore, partial z partial y is a function of both x and y in general. Of course, there may be cases, special cases, where you may not have this. That's another matter. Okay. Now, therefore, this derivative is called a partial derivative. So this is given at x. Similarly, you can ask the question, how does z change as a function of x for a fixed value of y? These are two different quantities or variations. One in which z is considered as a function of, z is varying with y when x is kept constant, and here z is varying with x when y is kept constant. In general, these partial differentials or derivatives are functions of both the independent variables x and y in general. Okay, this is something that you should remember. Now, you can take higher partial derivatives, because we just saw that partial z partial x and partial z partial y, keeping these variables constant, these are in general some functions of x and y. So we can take further partial differentials, right, just like we took for the original function. Now those are called higher order partial derivatives. So we can for example we can consider partial squared z by partial x squared, which is nothing but partial by partial x of partial z by partial x. Okay, so here when I take partial with respect to x, I am obviously keeping y constant in both these cases. Okay, now I can also consider partial by partial y keeping x constant of partial z by partial x keeping y constant. So that is called a mixed partial derivative, partial squared z by partial y partial x. Okay, and similarly one can also take partial by partial x at constant y of partial z by partial y, which itself was obtained by keeping x constant, that is partial squared z by partial x partial y. In general, if the first derivatives are smooth and continuous, then partial squared z by partial x partial y is partial squared z by partial y partial x. That is, these are called the mixed derivatives. These are called the mixed derivatives because they have derivatives with respect to both x and y, right? So in general, this is true if the function is smooth and continuous. Okay, so if the function z of x y and its derivative are smooth and continuous. Okay, now let's just take a very simple example to illustrate our idea. I'm sorry about this. Okay, let's take a new sheet. Okay, so what is an example? Let's consider the example z as which is a function of x and y, which is nothing but x cubed y minus e to the xy. So this is our function of two variables. The independent variables are x and y. Okay. Now, what is partial z by partial x? Oops, I'm sorry about this. Okay. So, if you ask the question what is partial z, sorry, let's choose a different color. Partial z by partial x constant y, that is nothing but when you do this partial differential, you're going to treat y as a constant. So you simply differentiate x and keep y as such. And here you will keep, if you differentiate e to the xy, you will get the same function e to the xy times the differential of the argument. Here y is constant, and if you differentiate x, you will just get 1. So you will get y e to the xy. Similarly, if you consider partial z by partial y at constant x, okay, here you have to keep y constant in the first, x constant in the first expression and differentiate with respect to y, and similarly you will have to keep x constant in the second expression and differentiate with respect to y. So these are something that you can do very easily. Just a quick recap of the same. Okay, now let's evaluate some mixed derivatives. Sorry about this. Okay. Let's consider partial squared f by partial x partial y, which is nothing but partial by partial x of partial f by partial y, and we already have this expression for partial f by partial y. Okay, so out here, I'm sorry, when I mean f, I mean z here. So if you want, I can quickly change the notation. Okay, let me just change the notation so that there's no confusion. Oops. We know what is partial z partial y. So when we do this, you will get 3x squared minus, now in the next term you have to differentiate with respect to x. So you have to first keep x as a constant and then differentiate the second one. You will get xy e to the xy. Then you will keep e to the xy constant and then differentiate x, and that's what you will get. Okay. Now you can verify yourself that if you do partial squared z by partial y partial x, you will get the same result. As I just told you, the mixed derivatives of smooth and continuous functions are often the same, right? So that's something that so partial squared z by partial x partial y is nothing but partial squared z by partial y partial x. Okay, this is something that's verified for this case. Okay, and we can similarly find other higher derivatives. Okay, now there is one important idea when we consider higher partial differentials, and that is the idea of what is called a total derivative, okay, or a total differential. Okay, so let's first understand that concept, the notion of total differential. Okay, now if I consider a function of two variables f of x, y, now I told you that there are two variations that one normally thinks of, that is variation of f with respect to x when y is kept constant, and variation of f with respect to y when x is kept constant. So these are two independent variations. Okay, so these variations are along the two coordinate axis, so to speak. Okay, now should be axis. Now what if you are not walking only along the x direction or only along the y direction. What if you take a point and then you walk a little bit in an arbitrary direction along delta x in the x direction and delta y in the y direction? Okay. What about the rate of change of f? Okay. What is the change in f if you walk a little bit away from a point x to x plus delta x and a point y to y plus delta y? What is the change in the function f? That is simply this quantity. That is, you have, okay, let me go to the next page. Okay, so you mainly have to find out, you have a point x, you have a point x plus delta x, y plus delta y, you have a point x, y. Okay, you're moving a little bit away from this point. Delta x and delta y are small in some sense. Okay, now so delta f is f of x plus delta x, y plus delta y minus f of x, y. So I'm going to do a trick. I'm going to add and subtract a same quantity, f plus delta x, y plus delta y minus f of x, y plus delta y plus f of x, y. Let me just plus f of, sorry about this, x, y plus delta y minus f of x, y. So if you look at it, I am essentially adding and subtracting the same term. So we are not changing the expression in any sense. Okay, so now let's go back to our derivation. So what I can do is I can think of delta f as f of x plus delta x, sorry, y plus delta y minus f of x, y plus delta y divided by delta x times delta x plus, I'm multiplying and dividing by delta x for the first two terms. If I consider the last two terms, f of x, y plus delta y minus f of x, y upon delta y times delta y. Okay, so I have done nothing difficult. I am just merely multiplying and dividing. So delta f, in the limit when delta x, delta y tend to 0, because these are infinitesimal or small quantities. Okay, therefore delta f is nothing but, now what can we say about this? Here we are changing only delta x. If you look at this expression, right, if you look at this expression, delta y, sorry, y is fixed at y plus delta y. So the only variable that is changing rather is x from x to x plus delta x, right? So f, delta f is, therefore this is nothing but the partial variation or partial derivative of f with respect to x evaluated at y plus delta y, okay, times delta x plus, here I am considering x is fixed at x, but y is changing from y to y plus delta y, right? So what I will do is I will write this as partial f by partial y at constant x times delta y. Okay, now when you consider these two quantities, okay, we know that this quantity within first order, see, we are now looking only terms that are accurate to order delta x and delta y. So this quantity can be replaced to be partial f by partial x at y itself. So delta f is nothing but partial f by partial x, okay, at constant y. Now in the limit when delta x, delta y tending to 0, delta x becomes the differential dx and delta y becomes the differential dy. Okay, This is the notation in calculus. When delta x delta y going to 0, you replace delta x delta y to be dx and dy. So partial f by partial y at constant x dy. Now similarly, we also will replace, instead of delta f, we will write it as df. Okay. Now this is a very useful and important concept. This is called the idea of a total derivative, or a total differential, I'm sorry. Total differential. What does this do? This merely tells you that if you have a function of two variables f of x, y, now how much does this function change if you simultaneously change x by an amount dx and y by an amount dy. Okay, and it tells you this change in terms of the changes along the respective coordinate axis, so to speak. Okay, so that is the idea of, so this is a very important idea in multivariable calculus. It's used often in thermodynamics. This is a very simple idea, merely an extension of what we normally do in single variable calculus to higher dimensions. Okay, now so this idea can be generalized to not just two variables. You can also generalize to functions of many variables, right? So what we do is you write df as, if I have a function f which is a function of x1, x2, x3, so on up to xn, then we'll write this as dx1 plus partial f partial x2 dx2 plus so on up to plus partial f partial xn dxn. Now when I do this, what I really imply is, when I take partial derivatives here, everything is except x1 is kept constant. Here everything except x2 is kept constant. Here everything except xn is kept constant. Okay, that's the meaning of course, partial derivatives. Okay, so this is a very important idea in partial differentials. Okay, now what we're going to do next is some very simple ideas in terms of expressing the function of two variables, okay, in terms of another set of two variables. Okay, so this is again a very useful tool that we often employ in thermodynamics and in transport phenomena. I'll take a very simple example. The example is, suppose I consider a function of two variables x and y. Let the function be x squared minus y squared, that is z. Now what are the independent variables here? The independent variables are x and y. Now I'm going to change from x to the polar coordinate r cosine theta, and from y to r sine theta. Okay, these are the polar coordinates in a plane. Okay, so we know that x squared plus y squared is equal to r squared times cos squared theta plus sine squared theta, which is r squared. Okay, this is something that you know. Now therefore z can be converted into x squared times cos squared theta minus sine squared theta, which is nothing but r squared times, you can write this as cos 2 theta, right? Cos square theta minus sine square theta is cosine of 2 theta. Now, so you have two representations of the same function. Here you have z as a function of x and y. Here the same z is now written as a function of r and theta. Okay, here z is a function of x and y. Now we can take partial derivatives in many ways. Now let's take some examples and illustrate this idea. Here first I'm going to consider partial z, oops, I'm sorry, I'm out of the by partial r at constant theta. Now if I need this, I have to first consider z as r squared times cos squared theta minus sin squared theta, because I need the dependent variables to be in terms of r and theta, which makes my job of evaluating this derivative very simple. So I'm keeping theta constant, so I have to differentiate only with respect to r. So this is very straightforward, right? It's something that you can do. Now instead I considered z as x squared minus y squared, which is nothing but I can rewrite this as 2x squared minus x squared minus y squared. So I'm adding and subtracting x squared. So this is 2x squared minus r squared. So this functional representation of z is a function of x and r. The independent variables are x and r. So if I take this functional representation and take a derivative with respect to r, keeping x constant, I'll get minus 2r. Similarly, I can do another trick. I can rewrite this function as x squared, minus instead of y squared, I'm going to write minus 2y squared plus y squared. Okay, so x squared plus y squared is r squared, so z will become r squared minus 2y squared. So now I can take partial z with respect to partial r, but keeping y as a constant, because this functional representative, the independent variables are r and y. Here it is r and x. So when I do this, the answer I will get is plus 2r. Now compare these two results. They are not the same, and it should not be surprising, because although this is partial z partial r, this is also partial z partial r. Now what is kept constant in these two different expressions are very, very different, right? Therefore the answer that you get is also very different. So this is a very important point that we must keep in mind when we do partial differentials, because this is something that you will get often confused, or you may get very erroneous and very paradoxical results if you don't keep in mind what is kept constant when you do a partial differential. You see, the same partial z partial r, when theta is kept constant, you got this result. When x is kept constant, you got minus 2r, and when y is kept constant, you got plus 2r. Okay, so all these three are very, very different results. So this is something that we have to keep in mind. Okay, so what I'll do next is to further illustrate this idea of total differential, okay, using one more extension of this example in plane polar coordinates. Okay, so here now what I'm going to do is I'm going to consider a function of two variables. Oops. Let me choose a different color. So I'm going to consider function of two variables, and I'm going to consider the change of these variables of this function from xy to r theta. This is often used or done in transport phenomena. Okay, now so if you have a physical variable which is a function of xy, by using this transformation you can change this function to function of r and theta. Okay, so df, the total differential, is nothing but partial f. If f is a function of r and theta, then df is partial f partial r at constant theta dr plus partial f partial theta at constant r d theta. Okay, now if you want partial f by partial x from this representation, if I have a function in this representation, getting partial f by partial x at constant y is trivial, because you have the function explicitly in terms of x and y. Now you have the function in terms of r and theta. So how do you get this information from this representation? The answer is straightforward. What you do is you use this total differential written here and differentiate this with respect to x plus partial f partial theta at constant r partial theta by partial x at constant y. Okay, so this is the idea. Now we can implement this, or we can illustrate this using this example. f of xy is equal to x squared minus y squared is equal to r squared times cos squared theta minus sin squared theta. Okay, this is what we just did, which is r squared cos 2 theta. Now df is partial df by d. Let me just go back a little bit. Let me do df dx at constant y from this representation, which is partial f partial r at constant theta times partial r by partial x at constant y plus partial f partial theta at constant r partial theta partial x at constant y. Now we know what is r, x squared plus y squared to the power half. So we can calculate what is partial r partial x at constant y, which is nothing but 1 over 2 2x upon x squared plus y squared whole to the half. Okay, just straightforward differentiation. But x squared plus y squared whole to this 2 and 2 will cancel out. Okay, let me cancel this out. Right, and x squared plus y squared is r squared, so this will be simply x by r. Similarly, you can verify partial r, or rather partial theta by partial x at constant y is nothing but minus sine theta by r. Okay, this is something that you can verify fairly easily. So what is the objective? The objective is to get partial f by partial x at constant y from the r theta representation of the function. So we know what the function is. So we know what is partial f partial r at constant theta, because we know the function. We know the representation of the function in r theta representation. So I can readily find these derivatives. Right, partial f partial r at constant theta is nothing but 2r cos 2 theta. Right, and we just found what is partial r partial x at constant y out here, but x by r is also cosine theta. Right, that is something we know from basic trigonometry. Okay, so now therefore you will find that this is nothing but 2r cos 2 theta cos theta plus 2r sin 2 theta sin theta. So if I take the 2r common and then you write cos 2 theta cos theta plus sin 2 theta sin theta, this is nothing but 2r times cos of 2 theta minus theta using cos A minus cos B formula. This is nothing but 2r cos theta. This is nothing but x is equal to r cos theta. This is something that we know. So let me write it properly. R cos theta. So this is nothing but 2x. Partial f partial x at constant y is 2x. Now if you had the knowledge of the function x squared minus y squared, then obviously you would know how to do this. That's not the issue. You will immediately say it's 2x. But what I'm trying to say is, even if you didn't know this, suppose this knowledge was not there with you, how do you calculate this using the information of the function in terms of r and theta? So that's what we discussed just now. You can use the principles of basic principles of partial differentiation, and therefore you can go ahead and calculate these kind of mixed derivatives when the functional representation also changes. Okay, that's a very, very interesting application. Okay, now there is one thing that I would like you to remember, which is that if x is r cos theta, r is x by cos theta. Okay, now if you ask the question, what is partial r partial x at constant y? Now r is x squared plus y squared to the half. So you can find what is partial r partial x at constant y. That is nothing but x by r, which is cos theta. Okay. Now if I do this, partial r partial x, I get 1 by cos theta. Now what's the catch? Here partial r partial x is cos theta, here partial r partial x is 1 by cos theta. Well, I deliberately hid this fact. When I differentiated this with respect to x, I'm keeping theta constant, whereas here I'm keeping y constant. Okay, so partial r partial x at constant theta is 1 over cos theta, whereas partial r partial x at constant y is simply cos theta. So there is no need for these two answers to be the same, because what is kept constant is very different. Here y is kept constant, here theta is kept constant. Okay, so this is something that is very, very important, although it seems rather straightforward when you think through it, but often this is the cause of many errors in derivations in thermodynamics and even in transport phenomena. Okay, so what I will do is I'll stop for now in this module, and I'll continue with exact and inexact differentials, partial differentials, in the next module. Okay, so until then, goodbye.